In example 2.25, we're going to find the slope of the tangent line to the ellipse 3y squared plus 2x squared equals 5 at the point -1, 1. And so this ellipse looks something like this. And we're saying that it goes through a point -1, 1. Sorry, that's over here. So -1, 1. And we're wondering what is the slope. And I'm guessing it's going to be something positive there. But we'll actually find the slope of the tangent line using implicit differentiation. So again, we use this whole process. We apply d dx to the entire equation, 3y squared plus 2x squared equals 5. And since the derivative respects addition, we can just apply d dx to each part. So this is d dx of 3y squared plus d dx of 2x squared equals d dx of 5. And so this equation is going to become, well, the derivative of 5 is 0. The derivative with respect to x of 2x squared is 4x. And now the derivative of 3y squared, remember you have to use the chain rule and think of y as a function of x. So that's going to be the derivative of y, which would be 6y. And then you have to multiply by dy dx. Okay, so you're thinking of the derivative of 3y squared with respect to y is 6y, and then you have to multiply by the derivative of the inside function, which is the y with respect to x. That's dy dx. So our equation becomes 6y dy dx plus 4x equals 0. Again, you need to move the terms that don't have dy dx over to the other side, and so you have 6y equals dy dx, and then finally you divide by the 6y to isolate the dy dx. So dy dx is negative 4x over 6y, and we're asked to find the slope of the tangent line at -1, 1, and so that means we want to find dy dx at the point -1, 1, and so that's -4, and x in that case would be -1, and that's over 6 times the y, and that y in that case is 1. So we're getting a slope of positive 4/6, which is equal to 2/3. Okay, so this line right here, this tangent line to the curve at -1, 1, has a slope of 2/3. That's our dy dx. And so you see now that when you're doing implicit differentiation, you have to know the x and the y value to calculate the derivative typically.